This video explores the topic of Internet of Things and Industrial Internet of Things within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. Big data in the Internet of Things is defined by volume, velocity, and heterogeneity. A single asset may produce KHZ vibration traces, low-rate temperature logs, and intermittent event logs. Globally, we are already operating at greater than 150 zettabytes of data across all domains. For industrial Internet of Things practitioners, this implies designing pipelines that handle high-frequency sampling, reliable time synchronization, and efficient feature extraction, fast Fourier transform, wavelets, statistical windows, before costly storage or cloud transfer. From the analytics viewpoint, benefits are concrete. Predictive maintenance models that reduce unplanned downtime and optimize spare parts logistics. But achieving them requires careful dataset curation, labeling strategies, and continuous monitoring of model drift. Characterizing Internet of Things data is crucial. Most industrial analytics operate on time series, often multimodal, vibration plus temperature plus operational state. A single camera or high-rate accelerometer can generate gigabytes per day. When multiplied across a production line, the aggregate reaches petabyte scale quickly. To be practical, architectures must both preserve raw traces for forensic analysis and create feature streams for real-time inference. Techniques such as timestamp normalization, precision time protocol for sub-millisecond sync, windowed fast Fourier transforms, and envelope analysis are fundamental tools for students to master. Now examine the standard 5 V's applied specifically to IoT and industrial IoT. In industrial IoT, we must treat the 5 V's pragmatically. Volume and velocity drive storage and compute decisions. Variety demands modality-specific preprocessing. Veracity forces us to instrument sensor health and calibration metadata, and value compels us to connect outputs to decisions that save money or improve safety. By 2030, richer sensing modalities will increase variety drastically, so learning to design adaptive sampling strategies and robust signal preprocessing, and to quantify uncertainty from sensors into model outputs, will be central skills for measurement engineers. Next, let's list the real sources of industrial IoT data and how they must be fused. Industrial IoT datasets are heterogeneous. Sensors sit alongside programmable logic controller event logs, manufacturing execution system batch records, and maintenance histories. For predictive maintenance, combining vibration spectra with recent maintenance actions and operation cycles makes models far more accurate. However, labeled failure events are rare, and data scientists often depend on engineered features and semi-supervised learning methods. By 2030, we expect digital twins and richer operational metadata to reduce ambiguity and support transfer learning between similar assets. We now turn to the analytics techniques used to convert these fused data streams into decisions. Analytics in industrial Internet of Things spans classical and deep learning approaches. For time series analysis, we commonly use long short-term memory networks, transformer models, or temporal convolutional networks. For vibration analysis, signals are converted to spectrograms and processed using convolutional neural networks, or hybrid convolutional neural network, recurrent neural network models. Production systems require streaming frameworks such as Apache Kafka with Apache Flink or Apache Spark, to process events in real time. Evaluations must be cost-aware. A false positive in safety systems has different consequences than a missed early warning for a bearing failure. Looking forward, tighter integration of physics-based models with machine learning is expected to improve trust and reduce data requirements, while on-device continual learning will help adapt models between maintenance cycles. Next, the software and platforms that make these analytics run in practice. Implementing industrial Internet of Things analytics requires a full stack: robust ingestion, message queuing telemetry transport / Apache Kafka, stream processors, Apache Flink, Apache Spark, and machine learning frameworks that can be optimized for the edge. In 2025, major cloud vendors will provide integrated Internet of Things platforms that simplify provisioning and pipeline management, while specialized edge toolchains enable model quantization and deployment to microcontroller units. By 2030, we expect more standardized cross-runtime toolchains, open neural network exchange and similar, and federated learning orchestration to reduce raw data movement and enable privacy-preserving fleet learning. Real industrial deployments show substantial benefits. When predictive maintenance is properly instrumented, organizations can report maintenance cost reductions in the approximately 18 to 25% range and large drops in unplanned downtime, case-dependent. The range reflects differences in baseline maintenance maturity and the quality of instrumentation and data pipelines. For master students designing experiments or proofs of concept, focus on measurable key performance indicators such as mean time between failures, mean time to repair, downtime hours, and maintenance cost per operating hour, and on embedding human review in the loop during early deployments. By 2030, many more mid-sized plants will adopt these methods. By 2040, expect much higher automation, guided by validated digital twins. Cloud computing remains the dominant architecture for scalable Internet of Things analytics and long-term data management. In 2025, the market will surpass $1,295 billion United States dollars, covering all layers of the stack, infrastructure, platforms, and software services. By 2030, forecasts indicate the market could reach $2,280 billion United States dollars, largely due to widespread industrial cloud adoption and artificial intelligence workloads. For industrial Internet of Things, the cloud enables advanced analytics, historical data storage, and lifecycle management across distributed sites. Now we'll explore specific cloud models and service types relevant to the Internet of Things and industrial Internet of Things. Cloud computing is structured into three layers: infrastructure as a service, platform as a service, and software as a service. Industrial Internet of Things primarily utilizes infrastructure as a service for raw compute, platform as a service for processing pipelines, and software as a service for visualization and asset management. The 2025 analysis shows software as a service accounting for nearly half of cloud spending, with platform as a service rapidly growing as enterprises modernize data architectures. The trend beyond 2030 will blur these boundaries as modular artificial intelligence and serverless computing become standard for Internet of Things workloads. Let's next identify why cloud adoption is so crucial for the industrial Internet of Things. Cloud computing provides massive scalability and reliability, critical for the Internet of Things' bursty and heterogeneous data flows. With multi-region redundancy, reliability is ensured. Beyond 2030, cloud architectures will become increasingly distributed, integrating regional edge zones to minimize latency and ensure compliance with local data regulations. For engineers, understanding how to design hybrid cloud edge systems will be essential for optimal performance and cost efficiency. Internet of Things cloud platforms like AWS IoT, Azure IoT Hub, and Google IoT Core offer integrated solutions for secure communication, data ingestion, storage, and visualization. They often include built-in artificial intelligence services for predictive maintenance, process optimization, and energy management. Such platforms simplify deployment, improve scalability, and reduce the complexity of managing thousands of devices. Security is a major concern because Internet of Things devices often operate in sensitive or industrial environments. Unauthorized access could cause operational failures or safety hazards. Cloud security mechanisms ensure encrypted communication, authenticated devices, and access control. Regular software updates prevent vulnerabilities. Ensuring data integrity and privacy is essential to maintaining trust and reliability in industrial operations. Next, we'll address the main challenges and limitations of relying on cloud infrastructures. Cloud systems provide scale but introduce latency and security trade-offs. While suitable for analytics and visualization, they cannot support the sub-millisecond control required in industrial automation. As of 2025, nearly 23% of cloud security incidents trace back to misconfigurations or improper credential management. Moving toward 2030 and beyond, policy and governance, especially around AI-generated data and model ownership, will become equally important as technical design choices. This leads to the complementary architecture, edge computing. Edge computing shifts data processing from centralized data centers to the network periphery, enabling real-time decisions and reducing latency. The 2025 market already exceeds $168.4 billion United States dollars, with industrial automation, automotive, and energy sectors leading adoption. By 2030, forecasts show over $248.96 billion United States dollars as edge AI chips in containerized runtimes become mainstream. In the long run, we expect seamless coordination between edge and cloud, forming distributed, mesh intelligence supported by 6G. Let's look closer at how edge computing supports industrial systems. Edge architectures organize computation hierarchically. Sensors send data to gateways for local preprocessing before selective transmission to the cloud. This architecture reduces bandwidth, latency, and privacy risks. Industrial projects increasingly adopt hybrid deployments. As of 2025, new systems implement both edge and cloud analytics. The long-term goal by 2040 is self-managing edge ecosystems, where workloads dynamically move based on resource availability and network health. Next, we'll examine key technologies driving edge AI inference on these platforms. The latest trend in industrial IoT edge systems is on-device intelligence, running neural models directly on gateways or microcontrollers. Hardware like Jetson and Coral enable SUB50 MS inference latency for computer vision or vibration analysis. By 2025, nearly half of new industrial edge systems include dedicated AI hardware, and by 2030 to 2040, low-power quantized models will be standard, with federated learning allowing global model improvement without centralizing data. Security, over-the-air firmware updates, and model integrity validation are indispensable for maintaining system reliability. Let's summarize how edge and cloud cooperate in modern industrial IoT systems. Modern industrial IoT deployments distribute computation. Edge devices perform real-time inference and preliminary analytics, while cloud infrastructure handles large-scale model training and cross-site insights. The glue between them includes robust communication, 5G, low-power wide-area network, and secure data orchestration, Kafka Spark. Forecasts to 2030 confirm simultaneous growth in both segments, edge computing for immediacy and cloud for scalability. The key engineering question is workload partitioning, deciding which data stays local and which should be aggregated for global optimization. In the next group of slides, we'll move into artificial intelligence and machine learning within IoT/industrial IoT. Edge AI moves intelligence close to data sources. In 2025, the edge computing industry already exceeds 168.4 billion United States dollars, driven by industry needs for millisecond response, cost reduction on connectivity, and privacy regulations. Typical deployment targets include microcontrollers for simple classification tasks and single-board computers, or embedded graphics processing units for heavier vision or machine learning workloads. For measurement engineers, important implications are model size, power envelope, real-time determinism, and the need for model optimization techniques, such as quantization and pruning, that preserve useful accuracy while meeting device constraints. By 2030, the trend toward tiny machine learning, i.e. tiny ML, and optimized runtimes will be far stronger, enabling many more autonomous functions at the device level. Next, we'll compare Edge AI and Cloud AI so you can choose the right place for computation. Edge AI and Cloud AI are complementary. The cloud offers the scale to train massive models with heterogeneous global data. The edge gives immediacy, vital for safety or control actions that cannot tolerate network delays. In practice, nearly all modern industrial IoT deployments use a hybrid pattern. Models are trained and periodically retrained in the cloud using aggregated telemetry, then optimized and pushed to edge devices for inference. Emerging directions to watch: federated learning and on-device continual learning in the period between 2025 and 2030, allowing models to adapt locally without central data transfer, lowering privacy and bandwidth pressures while maintaining adaptability. Let's see where Edge AI is used in real industrial scenarios. Edge AI shines in use cases where quick local decisions are required. Predictive maintenance is a prime example. Accelerometer or acoustic signals are processed locally to detect early fault signatures and initiate immediate protective actions. Vision systems running on Jetson or Coral-class devices perform inline quality control with tight latency bounds. Survey data shows predictive maintenance is on the strategic roadmap for most industrial firms, nearly 70% in recent surveys. For students, think about the signal processing chain, sensor, filter, feature model, and how to evaluate the end-to-end latency and false alarm trade-offs in practice. Now we'll examine platforms that make Edge AI development and deployment practical. Platform choice matters. Edge Impulse streamlines the end-to-end workflow for students and practitioners, from dataset capture to optimized deployment. TensorFlow Lite and TensorFlow Micro are the de facto runtimes for constrained devices. For production, Open Neural Network Exchange Runtime and Runtime Toolchains enable portability across vendors. By 2030, we expect standard model exchange formats and automated optimization pipelines to be common, minimizing vendor lock-in and accelerating deployment cycles. Let's summarize the concrete benefits Edge AI brings to industrial IoT and review a compact case study. Edge AI offers measurable operational benefits: rapid detection, substantial bandwidth reduction, and privacy preservation. In practice, galleries of proof of concept and production deployments report that sending only processed features or alerts to the cloud reduces upstream data by an order of magnitude or more, cutting costs and improving response times. For design projects, Quantify gains. Measure upstream bandwidth before and after edge filtering, track detection latency end-to-end, and estimate cost savings in storage and network bills. Imagine a factory motor equipped with vibration and temperature sensors connected to a Raspberry Pi running a lightweight machine learning model. When abnormal vibration is detected, the system triggers a local alert via buzzer, LED, or control signal, preventing damage. Meanwhile, summarized data is sent to the cloud for long-term analytics and maintenance planning. Next, we'll move from devices and edge AI to integrated spaces, smart environments, and how industrial IoT is applied at scale. Smart environments integrate sensing, connectivity, and intelligence to achieve operational goals. By 2025, digital transformation initiatives will have brought a majority of large organizations into at least early-stage smart environments, particularly in manufacturing and commercial buildings. For measurement engineers, building a smart environment means designing reliable sensing networks, ensuring time synchronization and data quality, and defining control policies that map analytics outputs to safe actuations. We'll next break down the components that make smart environments functional. A robust, smart environment combines hardware, software, and human processes. From accurate sensors and resilient connectivity to edge inference and cloud analytics, every layer must be designed to minimize latency, ensure data integrity, and provide clear operator feedback. Digital twins and augmented reality tools are becoming part of the operator's toolkit, increasing situational awareness and reducing mean time to repair. Finally, we examine how IoT integration is implemented in real-world smart environments. Real smart environments depend on robust integration patterns. Local preprocessors reduce noise and bandwidth, while the cloud aggregates cross-site data for deeper insight. Standards like Open Platform Communications Unified Architecture and Message Queuing Telemetry Transport are foundational. Open Platform Communications Unified Architecture for rich industrial interoperability and Message Queuing Telemetry Transport for lightweight telemetry. For engineers, practical tasks include building protocol bridges to legacy programmable logic controllers, maintaining accurate asset registries, and ensuring robust time synchronization to align events across systems. Industrial IoT transforms factories into proactive, self-optimizing environments. Predictive maintenance alone significantly reduces downtime and repair costs. Smart grids and energy management allow factories to dynamically balance energy use, often integrating renewables. Autonomous logistics and robotics further optimize processes. By 2040, nearly all industrial facilities are expected to leverage integrated Internet of Things systems for safety, efficiency, and sustainability. We'll discuss later how data from these systems flows into cloud and edge platforms for real-time decision-making. Smart environments are no longer a concept. They are a reality in modern industry and buildings. Integrating IoT with AI and automation allows organizations to respond in real time to environmental and operational changes. The benefits are tangible: energy savings, reduced downtime, improved safety and compliance. As IoT adoption grows, these environments will become fully autonomous by 2040, with AI-driven predictive optimization minimizing human intervention. The IoT landscape is evolving exponentially. By 2040, several tens of billions of devices will communicate seamlessly, powered by edge AI for instant decision-making. Connectivity advances like 6G and quantum communications will allow ultra-low latency, highly secure operations. Industries and cities will operate with unprecedented coordination, efficiency, and sustainability, reshaping everything from manufacturing to urban management. Artificial intelligence of things is the next step beyond traditional IoT, integrating intelligence directly into devices. It allows machines to learn from data, optimize their own operation, and anticipate failures. By 2040, artificial intelligence of things is expected to be standard across industrial systems, drastically reducing operational costs and improving efficiency while enabling autonomous decision-making. Next-generation connectivity is a game-changer for industrial and smart city applications. 5G already enables time-critical tasks, and 6G will extend these capabilities, making real-time autonomous systems feasible at a massive scale. Edge AI and network slicing combined with 5G or 6G will ensure high reliability, ultra-low latency, and secure operations for critical applications. Security and privacy are among the top challenges for IoT and industrial IoT adoption. Cyber attacks can cause operational downtime, financial losses, or safety hazards. Edge AI for threat detection, blockchain for device authentication, and robust compliance frameworks are critical. Investment in IoT cybersecurity is growing rapidly, with projections suggesting a quadrupling by 2035. By 2040, integrated security will be embedded in nearly all industrial IoT devices. In summary, IoT and industrial IoT are no longer experimental. They form the backbone of modern, intelligent industrial systems. Combining big data, cloud, and edge AI enables autonomous decision-making, operational efficiency, and sustainability. Looking to 2040, almost all industries will operate in highly interconnected, self-optimizing environments. This sets the stage for Industry 5.0, where humans and intelligent systems collaborate seamlessly. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Nice and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.